May 31st, 2013, the plains of central Oklahoma. The air is thick, heavy, electric, the kind of stillness storm chasers know not to trust. By sunset, the sky southwest of Reno will produce something no tornado before or since has matched. A funnel nearly 2.6 miles wide. Wider than Manhattan is at its broadest point. Wide enough that experienced meteorologists, watching it grow on radar in real time, will not believe what they're seeing. This is the story of the El Reno tornado, the widest ever recorded, and one of the most sobering lessons modern storm science has ever learned. To understand why El Reno happened, you have to understand the week that led up to it. Late May 2013 was already one of the most violent tornado stretches in recent American memory. Just 11 days earlier, an EF5 tornado had torn through Moore, Oklahoma, killing 24 people and leveling entire neighborhoods. The region was still grieving, still rebuilding, when the atmosphere began loading up again. By the afternoon of May 31st, forecasters at the Storm Prediction Center had issued a particularly dangerous situation tornado watch for central Oklahoma, a rare designation reserved for the most volatile setups. Warm, moist air was pooling at the surface, a powerful jet stream was overhead, all the ingredients were in place. Storm chasers from across the country, professionals, researchers, and amateurs with dash cams converged on the area. Some were there for science, some were there for the thrill. By nightfall, that convergence would prove tragic. At 6:03 p.m., a tornado touched down roughly 8 miles southwest of El Reno. At first, it looked unremarkable, a stovepipe funnel typical of the region. But this storm didn't behave like anything chasers had studied before. Instead of tracking in a single, predictable direction, it began to wobble, shifting from southeast to east to a sudden and violent turn northeast. That erratic path would matter enormously in the minutes to come, because it meant the storm was moving directly into the path of chasers who had positioned themselves based on where they expected it to go, not where it actually went. Within minutes, the tornado wasn't just turning, it was growing. Multiple smaller vortices, known as satellite tornadoes, began spinning up around the main circulation, some independently rated as strong as EF2. The parent tornado kept widening, swallowing the smaller vortices into itself. Then, as it neared US Route 81, it reached a size meteorologists had never documented, 2.6 miles across. To put that in perspective, a tornado that size could stretch from one end of a mid-sized town to the other with room to spare. It broke the previous width record set by a 2004 tornado in Hallam, Nebraska, and it remains the widest tornado ever measured to this day. A mobile Doppler radar unit, tracking the storm from close range, recorded winds inside the vortex reaching as high as 313 miles per hour. That's among the fastest wind speeds ever measured on Earth, second only to the 1999 Bridge Creek Moore tornado. Winds at that speed are, in theory, well into EF5 territory, the top of the tornado damage scale. And in fact, the National Weather Service initially rated El Reno an EF5 based on those radar estimates. But here's the twist that still generates debate among meteorologists. 3 months later, the rating was quietly downgraded to EF3. Why? Because the enhanced Fujita scale doesn't measure wind speed directly. It measures damage, specifically damage to buildings, and it infers wind speed from how structures failed. El Reno spent most of its life over open farmland. There simply weren't enough well-built structures in its path to register damage consistent with EF5 winds. The radar said one thing, the ground said another. It's a case still taught today as the clearest example of the gap between a tornado's true power and what the damage scale can actually capture. Some meteorologists still refer to it informally as a hidden EF5. For most of its life, El Reno tracked through rural land, sparing the town itself and the edges of the Oklahoma City metro from the worst of it. But rural doesn't mean empty, and it certainly didn't mean safe. The tornado's erratic growth caught chasers off guard in the most devastating way. A team of veteran researchers, Tim Samaras, his son Paul Samaras, and Carl Young, all part of the TwistX project, had spent years chasing storms specifically to deploy scientific instruments and improve tornado warnings. They were experienced, they were careful, and on that evening, the tornado's sudden, unpredictable turn overtook their vehicle. All three were killed. It marked the first time professional storm chasers had died in the line of their research. A fourth chaser, an amateur named Richard Henderson, was also killed. In total, the tornado claimed 8 lives.